So you might wonder, why did the student not include the nitrogen monoxide in their rate law? Well, here is the student's reasoning. So the student claimed that since NO does not appear in the equation for the overall reaction, then NO cannot appear in the rate law. Well, we know that there is a mistake because in part A of this question it says, explain why the student's rate law and reasoning are incorrect. Welcome to AP Chemistry Review and Practice. My name is Michael Farabaugh, and I'll be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Each episode will include answers and explanations to practice problems, along with advice to help you avoid common mistakes. So, are you ready to review and practice for the AP Chemistry exam? I hope so, because this lesson starts right now. Welcome back to AP Chemistry Review and Practice. In this lesson, I'll give you the chance to review and practice topics 5.8 to 5.11. As you can see on this slide, these topics fall under Unit 5 in the AP Chemistry curriculum, Kinetics. You can add your comments and questions below this video, and you can also email me with your comments and questions at apchemistryreviewandpractice@gmail.com. Check out the links in the video description area, which include the link to the packet that accompanies this video. Now let's move on to the review for topic 5.8, Reaction Mechanism and Rate Law. Here is an essential knowledge statement from the AP Chemistry course and exam description. For reaction mechanisms in which each elementary step is irreversible, or in which the first step is rate limiting, the rate law of the reaction is set by the molecularity of the slowest elementary step, that is, the rate limiting step. And now let's move on to the practice for topic 5.8. This is question 1. In question 1, we are given a balanced chemical equation, and it says substance QX reacts with substance Y2 to produce Q2 and XY2 as represented by the equation shown above. In part A, it says, in terms of particle collisions, explain why this reaction is unlikely to occur in a single elementary step. So the way we can answer this question is based on something that I had presented in an earlier episode of AP Chemistry Review and Practice when I was reviewing topic 5.4, Elementary Reactions. One of the essential knowledge statements for topic 5.4 is that elementary reactions involving the simultaneous collision of 3 or more particles are rare. So that's going to be how we answer part A of this question. I can see 4 particles of reactants, and so therefore this reaction is unlikely to occur in a single elementary step because the simultaneous collision of 4 particles is a rare event and not likely to occur. So we are given a proposed reaction mechanism in part B. Let's take a look at part B. So in part B, it says a proposed mechanism for this chemical reaction is shown below. And then in part I of part B, it says identify all of the substances that behave as intermediates in the proposed mechanism. So you might remember from an earlier episode of AP Chemistry Review and Practice, an intermediate is a substance that is produced in one step and is consumed in a later step of the mechanism. Let's go ahead and start with step 1, and we can see that substance Q2X2 appears as a product in step 1, and then also is consumed as a reactant in step 2. So that's an intermediate. And then looking on the right side of the equation in step 2, we can see that substance Q2X is produced as a product in step 2, and is also consumed as a reactant in step 3. So those 2 substances are going to be our intermediates, and that would be Q2X2 and Q2X. Now let's take a look at part B double I, and it says, after performing a kinetics experiment, a chemist observes that the reaction is zero order with respect to Y2. So which step of the proposed mechanism is most likely to be the rate determining step? Justify your answer in terms of the mechanism and the chemist's observation regarding Y2. Now, in topic 5.8, we are focusing our attention on the slow elementary step, the rate limiting or the rate determining step. And so if we focus our attention on that slow rate determining step, then let's think about the answer to this question. Do we focus our attention on the reactants that appear in the steps that occur after the slow rate determining step? And the answer to that question is no. If the first step of a mechanism is the slow step, then we write a rate law that only contains the reactant particles in the slow step. We do not consider any additional reactant particles that occur after the slow rate determining step. So it's that slow rate determining step that we use when we write the rate law, and nothing after the slow step. So now a chemist observes that this reaction is zero order with respect to Y2. So if the reaction is zero order with respect to Y2, then that means that Y2 does not appear in the slow rate determining step of the mechanism. So I can see Y2 as a reactant in step 2 and step 3. So therefore, by default, if step 2 and step 3 cannot be the slow rate determining step, then step 1 of this mechanism must be the slow step. So this is what I wrote for my answer to part B double I of this question. I said that step 1 of the mechanism is most likely to be the rate determining step, since the substance Y2 does not appear in the rate law, that is, the reaction is zero order with respect to Y2, then Y2 must appear in the fast steps that occur after the slow rate determining step. And now we have a carryover from part B double I to part B triple I, which says, write the rate law for this reaction that is consistent with your answer to part B double I. And so we're going to focus our attention on that slow step, step 1. And you'll notice that there are exactly 2 particles of QX as reactants and nothing else. So the only substance that will appear in the rate law is substance QX, but we do have to consider the molecularity, which means the number of particles or the number of molecules of substance QX. So because I see 2 particles of QX as reactants in that slow step 1, then our rate law should be second order with respect to QX. So this is my rate law. Rate equals the rate constant K times the concentration of QX squared, because this rate law should be second order with respect to QX. All right, well, those are the answers to question 1 of this packet. Now, let's take a look at question 2. In question 2, it says, the following mechanism is proposed for the conversion of O3, which is known as ozone, into O2, molecular oxygen, in the presence of NO, which is nitrogen monoxide. So we are given a 2-step mechanism, and we are also given the equation for the overall reaction. A student was asked to write a rate law for the overall reaction that is consistent with the proposed mechanism, and the student wrote the following response. So their rate law is rate equals the rate constant K times the concentration of ozone, or O3. Now, when you're talking about the slow rate determining step, then we should, looking at the mechanism, focus our attention on the reactants that appear in the slow rate determining step. So in this 2-step mechanism, step 1 is the slow step. Now I see 1 molecule of ozone, or O3, but I also see 1 molecule of NO, or nitrogen monoxide. So you might wonder, why did the student not include the nitrogen monoxide in their rate law? Well, here is the student's reasoning. So the student claimed that since NO does not appear in the equation for the overall reaction, then NO cannot appear in the rate law. Well, we know that there is a mistake because in part A of this question it says, explain why the student's rate law and reasoning are incorrect. Now, in question 1, we saw examples of substances in the mechanism that behaved as an intermediate, where they were produced in one step and then consumed in a later step. But here in question 2, we can actually see a substance that behaves as a catalyst. So a catalyst is a substance that is consumed in step 1 and then is regenerated in a later step of the mechanism. So take a look at the nitrogen monoxide. It appears as a reactant in step 1, and then it is regenerated as a product in step 2. So therefore, nitrogen monoxide, or NO, behaves as a catalyst. A catalyst is added to the reaction vessel at the beginning of the experiment. So therefore, the initial concentration of a catalyst is known. And although it is true that a catalyst does not appear in the equation for the overall reaction, a catalyst can appear in the rate law for the reaction. So this was the students' mistake. They assumed that we're not supposed to include the nitrogen monoxide in the rate law because it doesn't appear in the overall reaction. But again, the initial concentration of a catalyst is known, and it should appear in the rate law if it appears as a reactant in that slow rate-determining step. So explain why the student's rate law and reasoning are incorrect. So the initial concentration of a catalyst is known, and if a catalyst appears in step 1, and that is the slow rate-determining step of a mechanism, then the catalyst should appear in the rate law. Changing the initial concentration of the catalyst affects the initial reaction rate, so it definitely should appear in the rate law. So now let's take a look at the next part of question 2, which is write the rate law that is consistent with the proposed mechanism. So again, I'm going to focus on the molecularity, which is I see 1 molecule of O3 and I see 1 molecule of NO. So the slow step of the mechanism has 1 particle of O3 and 1 particle of NO as reactants. So therefore, the rate law should be first order with respect to O3 and first order with respect to NO. So this is the rate law. Rate equals the rate constant K times the concentration of O3 times the concentration of NO. All right, well, those are the answers to question 2. Now let's take a look at question 3, which is a multiple choice question. In question 3, we are given a 2-step mechanism, and this question asks, which of the following represents a rate law for the overall reaction that is consistent with the proposed mechanism shown above? So again, we're going to focus our attention on that slow rate-determining step, which in this case is step 1. And we are focusing on the molecularity, or the number of molecules or particles of the reactants that appear in the slow step. So the slow step of this mechanism has 1 particle of D2 and 1 particle of XQ as reactants. Therefore, the rate law should be first order with respect to D2 and first order with respect to XQ. So that makes choice A the correct rate law and the correct answer to question 3. Now, if you're watching the examples that I've shown you so far in this video, you might be wondering if step 1 of the mechanism will always be the slow step. In other words, is there an example of a mechanism in which step 2 is actually the slow step? Well, you're in luck because that is our next topic in Unit 6. So now it's time to move on to the review for topic 5.9, which is called pre-equilibrium approximation. So in this essential knowledge statement from the AP Chemistry course and exam description, it says, if the first elementary reaction is not rate limiting, approximations such as pre-equilibrium must be made to determine a rate law expression. And now let's move on to the practice for topic 5.9. This is question 4, which is also a multiple choice question. In question 4, it says, a proposed mechanism for a chemical reaction is shown above. Which of the following rate laws is consistent with this mechanism? Now, you'll notice right away that step 1 is not the slow step of this mechanism. Step 1 is actually a fast step, and it's a fast equilibrium. You can see double arrows in step 1, so that indicates that that's an equilibrium. So that's a fast equilibrium. And step 2 is the slow rate determining step. Now, if I just focus on step 2, I can see that the slow step of this mechanism has one particle of AQX2 as a reactant. So now what I'm going to do is I'm going to write the rate law just based on that particular reactant. So I'm going to write rate equals the rate constant K times the concentration of substance AQX2. Now, if you look at the 4 answer choices listed in question 4, you will see that that is not the correct rate law. So what's the problem with writing this rate law using AQX2 in my rate law? Well, the problem is that the substance AQX2, which appears as a product in the fast equilibrium of step 1, and then it's consumed as a reactant in the slow rate determining step 2, the substance AQX2 behaves as an intermediate in this mechanism. And so the problem is that the initial concentration of AQX2 is unknown. And since the initial concentration is unknown, it cannot be included in the rate law. So what do we do now? Well, I can tell you that in my video for topics 5.4 to 5.11, and I have included a link to that video in the video description area, I did present a general strategy for solving this type of problem. So when you have a fast equilibrium in step 1, followed by a slow rate determining step of step 2, there is a general strategy for doing a substitution procedure involving a little algebra. So if the rate law contains a substance that is an intermediate, then we need to replace that intermediate. So an intermediate cannot appear in the rate law for the overall reaction, and that's essentially what topic 5.9 is all about, the pre-equilibrium approximation. So again, you can check out that video where I give you the general strategy for how to remove the intermediate from the rate law. So now back to question 4, I'm going to go ahead and apply that procedure right now. So the first thing I'm going to do is talk about step 1, which is that fast equilibrium step. So because step 1 is a fast equilibrium, then the rate of the forward reaction, so from left to right, is equal to the rate of the reverse reaction from right to left. So I'm going to write the rate law for the forward reaction as rate constant K, so K forward, times the concentration of AQ times the concentration of X2, because I see one particle of AQ and one particle of X2 on the reactant side in step 1, but then that would equal the rate of the reverse reaction, which would be a different rate constant for step 1, so the reverse, and then times the concentration of AQX2. Now here comes the algebra, here comes the substitution procedure. So I'm going to solve for the concentration of AQX2 like this. All I did was I divided both sides of the equation by that K reverse rate constant, and now here comes the substitution procedure. So there is my rate law. Rate equals K times the concentration of AQX2. So that is the intermediate that I'm trying to get rid of. And now, as you can see on this slide, I'm going to take all of that information that's in that large red rectangle and plug it in for the concentration of AQX2. Now, when I do that, I'm going to get a combined rate constant, which I'm just merging into one universal rate constant for this rate law. So all of those K values are different, but they're all getting merged together. So I have now done that substitution procedure, and I get rate equals a rate constant K times the concentration of AQ times the concentration of X2. Now look at the 4 answer choices in question 4, and hopefully you can see that choice A is the correct answer. So to summarize what I did in this substitution procedure, using algebra, we have essentially replaced the intermediate AQX2 with the reactants from the fast equilibrium in step 1. Now, before we take a look at the next question in this packet, what I'd like to do now is to show you another similar problem that is related to topic 5.9. So what I'm showing you on this next slide, this comes from the 2019 AP Chemistry free response questions. And this was free response question number 6. And I have included in the video description area a link to the 2019 AP Chemistry free response questions along with the official scoring guidelines for those questions. So in question 6, we're going to see a similar example that applies to topic 5.9, the pre-equilibrium approximation. So in this question, which again is question 6 from the 2019 AP Chemistry free response questions, it talks about the decomposition of NO2, or nitrogen dioxide. So students are given a balanced chemical equation for the decomposition of NO2, and then they are presented with 3 different graphs. So on the x-axis of these graphs, we see time in seconds, but then on the y-axis of these graphs, it's either concentration of NO2, or 1 over the concentration of NO2, or the natural log of the concentration of NO2. And hopefully you can see, even from this far away view of these graphs, that one of them is a linear graph. Now in part A of this question, it says explain how the graphs indicate that the reaction is second order. Let me go ahead and zoom in a little bit more closely on these 3 graphs. So again, you can see concentration of NO2 versus time, 1 over the concentration of NO2 versus time, and then the natural log of the concentration of NO2 versus time. And so it's that middle graph, the 1 over the concentration of NO2 versus time, that's the one that is linear. So again, in part A of this question, it says explain how the graphs indicate that the reaction is second order. So the official scoring guidelines are the following. The linear graph of 1 over the concentration of NO2 versus time indicates a second order reaction. And in part B of this question, all they had to do was write the rate law. So it says in part B, write the rate law for the decomposition of NO2, and that would simply be based on that second order kinetics, rate equals the rate constant K times the concentration of NO2 squared. But now when we get to part C of this question, it is part C of this question that is very relevant to topic 5.8, reaction mechanism and rate law, and topic 5.9, the pre-equilibrium approximation. So take a look at part C of this question. Part C says, consider 2 possible mechanisms for the decomposition reaction. Now, in each of these mechanisms, the student has to answer the following question, which is the rate law described by this mechanism consistent with the rate law that you wrote in part B? So take a closer look at mechanism 1. Do you see the slow step? Step 1 is the slow step. So that would be relevant to topic 5.8, reaction mechanism and rate law. And now take a closer look at mechanism 2. Do you see where the slow step is? Yes, it's actually step 2. So we have step 1 is that fast equilibrium that I talked about, and then step 2 is the slow step. So that would be relevant to topic 5.9, the pre-equilibrium approximation. So what I'm going to do as we process the information here in part C is that I'm going to show you the official scoring guidelines answer, and then I will also show you sample student responses that either did earn the point or did not earn the point. Let's go ahead and take a look at part C, mechanism 1. So in part C, mechanism 1, we can see that step 1 is the slow step. So the slow step of the mechanism has 2 particles of NO2 as reactants. So therefore, the rate law should be second order with respect to NO2. And so yes, that is consistent with the rate law that was written in Part B. Rate equals the rate constant K times the concentration of NO2 squared. Now, here is the official scoring guidelines answer for Part CI. It says, yes, based on mechanism 1, step 1 is the slow rate determining step. So therefore, the rate law of this elementary reaction is rate equals the rate constant K times the concentration of NO2 squared, which is consistent with the second order rate law in Part B. And now I'm going to show you two student responses, one that did earn the point and one that did not earn the point. Let's take a look at this student response. The student said, yes, the rate law described by mechanism 1 is consistent with the rate law written in Part B because the rate limiting step is the slow step. And the slow step in mechanism 1 yields a rate of rate constant K times concentration of NO2 squared. And so the commentary about this student response is the following. In Part CI, the student writes that the slow step in a mechanism is the rate limiting step. The student correctly writes the rate law for step 1 of the mechanism as rate equals rate constant K times NO2 squared, and states that it is consistent with the experimental rate law written in Part B, and the point was earned. Now let's take a look at another student response that did not earn the point. So this student said, yes, the slow step or rate determining step is consistent with the rate law with respect to NO2, which is second order. And the commentary about this student response is, in Part CI, the student writes that the slow step or rate determining step is consistent with NO2 being second order. However, the student does not write the rate law for this mechanism, and so the point was not earned. Now, on this slide, you can see an excerpt from the Chief Reader Report for the 2019 free response questions. And so on the right, responses that demonstrate understanding for Part CI are yes. Step 1 is slow, therefore it is the rate determining step of this mechanism. The rate law of this elementary reaction is rate equals rate constant K times concentration of NO2 squared, which is consistent with the second order rate law in Part B. And on the left of this slide, you can see some common misconceptions or mistakes. So stating that the proposed mechanism follows a second order rate law without referring to the molecularity of the slow rate limiting step. Another mistake was simply adding the individual steps of the mechanism to generate the original reaction, and then stating that the process is second order because the stoichiometric coefficient for NO2 is 2. So we don't get the rate law by looking at the coefficients for the balanced equation for the overall reaction. So that was a mistake. Now, the next part for topic 5.9, pre-equilibrium approximation, is that mechanism in which step 1 is a fast equilibrium, and then step 2 is the slow step. So I'm going to use that substitution procedure that I showed you in question 4 of this packet. So the slow step of this mechanism has 1 particle of N2O4 as a reactant. So this is my rate law. Rate equals the rate constant K times the concentration of N2O4. So that was that issue that I had mentioned earlier where we cannot have an intermediate in the rate law. And so N2O4 is an intermediate. So the substance N2O4 behaves as an intermediate in this mechanism, and the initial concentration of N2O4 is unknown. So therefore, N2O4 cannot be included in the rate law. So here's that substitution procedure that I showed you earlier. So remember that step 1 is that fast equilibrium. The rate of the forward reaction is equal to the rate of the reverse reaction. So the forward reaction would be rate equals rate constant K for the forward reaction times the concentration of NO2 squared, because I see 2 particles of NO2 as reactants in step 1. And then for the reverse reaction, so going in the opposite direction, that would be the rate constant K for the reverse times the concentration of N2O4. Here comes the algebra where I rearrange that equation. And then I take this expression for N2O4 and I plug it in to the rate law for step 2. And I'm doing this because we need to remove the intermediate from the rate law. And when I do that, I combine all of those K values together into one combined rate constant K. But now you can see that I have replaced the N2O4 with NO2 squared. So using algebra, we have essentially replaced the intermediate N2O4 with the reactants from the fast equilibrium in step 1. Here is the official scoring guidelines for part C, Roman numeral 2, from question 6 of the 2019 free response questions. Now there's something in this answer that might not make sense to you right now if you're going in order. So there is a large K or a capital K, and that's actually an equilibrium constant, but equilibrium is unit 7. So at this point, we're in the middle of unit 5. You might not quite understand what an equilibrium constant is because we haven't gotten to unit 7 yet in this series for AP Chemistry Review and Practice. But either way, I can tell you that if you do a substitution procedure to effectively replace the N2O4 with 2 molecules of NO2 or NO2 squared, then that is an acceptable method for saying that yes, step 2 is slow, therefore step 2 is the rate determining step of this mechanism, and then they do that substitution procedure, and you can see that that substitution procedure was part of the official scoring guidelines in this question. Now I'm going to show you some student responses that either did earn the point or did not earn the point. So take a look at this student response. They said, yes, it is, because the slow step yields a rate of K times N2O4. And they say, however, N2O4 is an intermediate. And then they talk about the equilibrium equation, and they do that substitution procedure. We find that the rate is equal to, and there's all those Ks, K1, K2, K3, times concentration of NO2 squared. And so they say, yes, we get the rate equals K times NO2 squared. So here's the commentary showing that this student did earn the point. It says, in part C, Roman numeral 2, the student correctly identifies N2O4 as an intermediate in the mechanism, and they write a rate law for the slow step as rate equals rate constant K times concentration of N2O4. The student correctly notes that for an equilibrium system, the rate of the forward reaction equals the rate of the reverse reaction, and then they do that substitution procedure. The student correctly combines the rate constants into a single rate constant and notes that the rate law is consistent with the second order rate law from part B. So yes, the point was earned. And now I'm going to show you a couple of student responses that did not earn the point. So this student actually disagrees and says, no, for mechanism 2, the rate law relies on the slow step, and they stop basically saying that it doesn't work because rate equals K times concentration of N2O4, and they say that's not the same as the rate law that was written in part B. So the commentary is that here the student states incorrectly that the rate law for mechanism 2 is not consistent with the rate law from part B. The student does not identify N2O4 as an intermediate, and so the point was not earned. Here's another example of a student response that did not earn the point. They say, yes, the slow step indicates that the concentration of N2O4 is first order. They say N2O4 is not in the rate law, so we need to translate it in terms of NO2. Now, I underlined the mistake that they made, so take a look at this next sentence. In step 1, 1 mole of N2O4 is equal to 2 moles of NO2. Now, that's not algebra, that's just a simple statement indicating that they're replacing N2O4 with 2 moles of NO2. So the commentary is that The student does indicate that the rate law for the mechanism is first order with respect to N2O4. They correctly comments that N2O4, which happens to be an intermediate, is not part of the rate law. However, the student just simply states that 1 mole of N2O4 is equal to 2 moles of NO2, and this statement cannot be used as a justification for declaring this reaction to be second order with respect to NO2. So there's no algebra, there's no substitution, there's simply a statement that we're going to replace N2O4 with 2 moles of NO2, and that is not earning the point. So on the Chief Reader Report for 2019, again, you can see on the right side responses that demonstrate understanding. They refer to the step 2 being the slow rate determining step. They make a comment that because N2O4 is an intermediate, it cannot appear in the rate law, and they do that substitution procedure. But here are some mistakes that students made. Simply stating that the proposed mechanism follows second order rate law without referring to the molecularity of the slow step. Referring only to the stoichiometric coefficient of 2 in the overall balanced equation. So you can't just look at the stoichiometry of the overall balanced chemical equation. And then making some sort of invalid substitutions like N2O4 is equal to 2 molecules of NO2. That would not earn the point. So again, to summarize for topic 5.9, the pre-equilibrium approximation, if you ever have a situation on the AP Chemistry exam where the first step is a fast equilibrium and the second step is the slow step, then you have to do that substitution procedure. So the forward reaction rate is equal to the reverse reaction rate. Do a little bit of algebra, and then you effectively are replacing that intermediate with the reactants from the fast equilibrium in step 1. But you have to show how you do that substitution. So again, that would be topic 5.9, the pre-equilibrium approximation. Well, hopefully all of that made sense, because now we are ready to move on to the review for our next topic. This is topic 5.10, multi-step reaction energy profile. Here is an essential knowledge statement from the AP Chemistry course and exam description. Knowledge of the energetics of each elementary reaction in a mechanism allows for the construction of an energy profile for a multi-step reaction. So now let's take a look at the practice for topic 5.10. This is question 5. In question 5, it says the reaction, so 2xy plus y2 produces 2xy2. That reaction is endothermic. A proposed mechanism for this reaction is shown below, and we can see a two-step mechanism where step 1 is the slow step and step 2 is the fast step. And it says which of the following energy profiles is most consistent with the endothermic nature of the reaction and the proposed mechanism. So the first thing I'm going to do is focus on the endothermic nature of the reaction. Now, in an earlier lesson in AP Chemistry Review and Practice, I talked about these energy profile diagrams, and I said that if the energy of the products is less than the potential energy of the reactants, that would be an exothermic reaction. But on the other hand, if the potential energy of the products is greater than the potential energy of the reactants, that is an endothermic process. Let's go ahead and see if we can find some diagrams where the potential energy of the products is greater than the potential energy of the reactants. Well, it looks like choices A and B would be classified as endothermic because the potential energy of the products is greater than that of the reactants. And then looking at the energy profiles for choices C and D, we can see that those would be classified as exothermic because the potential energy of the products is actually less than that of the reactants. Now, we know we're looking for an endothermic reaction, so we can go ahead and eliminate choices C and D. Now what I have to do is focus on the fact that step 1 is slow and step 2 is fast. Now, we can see a difference in the appearance of the energy profile for choice A and choice B, and the higher the activation energy is, the slower the reaction rate is. So that hill is either a small hill and a big hill in choice A, or it's a big hill and a small hill in choice B, where that hill would represent the magnitude of the activation energy. So looking at choice A, I can see small hill and then big hill, and that would indicate first a fast step followed by a slow step. So the correct answer is not going to be choice A because we're looking for step 1 is slow and step 2 is fast. So looking at choice B, we can see big hill followed by small hill. So large activation energy followed by small activation energy. So that would be a slow step and then a fast step. So step 1 is slow, step 2 is fast. Therefore, that makes choice B the correct energy profile that is not only consistent with the endothermic nature of the reaction, but it also addresses the fact that step 1 is slow and step 2 is fast. All right, well, that's the answer to question 5. Now let's take a look at question 6. Here in question 6, we are also given an energy profile, and it says, draw a vertical line with a double-headed arrow on the reaction energy profile shown below that corresponds to the activation energy for the rate-determining step in the reaction mechanism. Now, I can put an arrow on this diagram for the activation energy of step 1, and I can also put an arrow on this diagram for the activation energy of step 2. But in question 6, we don't need to draw 2 double-headed arrows. We have to focus our attention on the rate-determining step in the reaction mechanism. So what's the rate-determining step? Well, the rate-determining step is the slow step. And it looks like it's going to be large activation energy followed by small activation energy, or big hill followed by small hill. That would be a slow step and then a fast step. But the slow step is the rate-determining step. So the higher the activation energy is, the slower the reaction rate is. So the correct answer to question 6 is just this double-headed arrow indicating that step 1, with a larger magnitude of its activation energy, would be the slow rate-determining step in this mechanism. All right, well, that is the answer to question 6. Now it is time to move on to the review for our last topic in this lesson, and that is topic 5.11, catalysis. Here are some essential knowledge statements from the AP Chemistry course and exam description. In order for a catalyst to increase the rate of a reaction, the addition of the catalyst must increase the number of effective collisions and/or provide a reaction path with a lower activation energy relative to the original reaction coordinate. In a reaction mechanism containing a catalyst, the net concentration of the catalyst is constant. However, the catalyst will frequently be consumed in the rate-determining step of the reaction, only to be regenerated in a subsequent step in the mechanism. Some catalysts accelerate a reaction by binding to the reactants, and the reactants are either oriented more favorably or react with lower activation energy. And there is often a new reaction intermediate in which the catalyst is bound to the reactants. Many enzymes function in this manner. Some catalysts involve covalent bonding between the catalyst and the reactants. An example is acid-base catalysis, in which a reactant or intermediate either gains or loses a proton. This introduces a new reaction intermediate and new elementary reactions involving that intermediate. In surface catalysis, a reactant or intermediate binds to or forms a covalent bond with the surface, and this introduces elementary reactions involving these new bound reaction intermediates. Now it's time to move on to the practice for topic 5.11. This is question 7. In question 7, it says, The potential energy diagram for an uncatalyzed chemical reaction is shown above. A student was asked to draw the energy profile for the reaction as it occurs in the presence of a suitable catalyst. The student's drawing, solid line, is shown in the box below on the left. So what the student did is they drew a line in which everything is lowered. Not only the activation energy for the reaction has been lowered, but they also lowered the energy of the reactants, and they lowered the energy of the products. So in part A of this question, it says, identify the error in the student's drawing. So the presence of a catalyst in the reaction mixture does not affect the following. It does not affect the energy of the reactants, it does not affect the energy of the products, and it does not affect the difference in energy between the products and the reactants. So the error in the student's drawing is that their curve for the energy profile of the catalyzed reaction pathway shows a decrease in the energy of the reactants and the products. And so that is what is incorrect. Now, we have to correct the student's mistake. So in part B, it says in the box on the right, correct the student's mistake by drawing the energy profile for this reaction that occurs in the presence of a catalyst. So let's keep the energy of the reactants and the products the same as in the original uncatalyzed reaction pathway. So something like this. So your curve for the catalyzed reaction might look something like this, that the catalyzed reaction pathway should show the same energy level for the reactants and the products as in the original curve. And the catalyzed reaction pathway should have a lower activation energy than the uncatalyzed reaction pathway. All right, well, that is the answer to question 7. Now, let's take a look at question 8. In question 8, it says the graph above shows a distribution of the collision energies of AX molecules for the reaction 2AX produces A2X2, and that reaction occurs at 100 degrees Celsius. The rate of this reaction increases when a suitable catalyst is added to the reaction mixture. And the question asks, which of the following shows how the appearance of this graph would be affected if the reaction is carried out at 100 degrees Celsius in the presence of a catalyst? Now, as you're looking at this diagram here in question 8, this might be familiar to you from something I had presented in a previous episode of AP Chemistry Review and Practice. So what you're seeing on this next slide, this was from the 2017 AP Chemistry exam, and in this question, it was about changing the temperature. So it's showing that the actual graph was from 120 degrees Celsius, and the student had to draw a second curve to show what would happen if the temperature was decreased to 30 degrees Celsius. Now, back to this question, we are not changing the temperature. So this is a different type of situation. And you can tell that we're not changing the temperature because it says 100 degrees Celsius, and then it says also at 100 degrees Celsius, but now in the presence of a catalyst. So why am I mentioning that the temperature remains constant? And the reason why is because now we can go look more closely at the 4 choices in question 8, and we can eliminate some wrong answers. Because since the temperature remains constant, the appearance of this Maxwell-Boltzmann distribution curve should not change. I'm going to go ahead and start with choice A, and if we can see a difference in the appearance of the Maxwell-Boltzmann distribution curve, then that would imply a different temperature, and we can eliminate that as our choices. So let's start with choice A. Hopefully you can see how different that curve appears. So it looks like they tried to change the temperature in the appearance of that curve in choice A. So in choice A, the appearance of the Maxwell-Boltzmann distribution curve has changed, so we can eliminate choice A. Now look at choice B. It looks like they tried to change the temperature. That curve looks broader and flatter. So again, we can eliminate choice B because the appearance of the Maxwell-Boltzmann distribution curve has changed. So we have four choices. We know it's not A and it's not B. So now it's either C or D. Let's focus on what is changing, and it's going to be the location of that activation energy, that vertical line on the x-axis. So let's compare the diagram in choice C with the original curve. Can you see what happened? Looks like the activation energy has been shifted to the right. And you can also see that there's a smaller portion to the right of the activation energy. There's a smaller fraction of particles that have enough energy to overcome the activation energy. So I'm going to show you why we can eliminate choice C. So with a catalyst, we expect the activation energy to actually be decreased. So in choice C, that line, that vertical line that represents the activation energy for the reaction, has actually been moved to the right. So this shows an increase in the activation energy, and that's not what would happen with the presence of a catalyst. And so now you can see to the right of that line, a smaller fraction of the collisions have enough energy to overcome the activation energy barrier. So that would not lead to a faster reaction rate. We can definitely eliminate choice C. Now look at the details in choice D. Look at the location of that vertical line representing the activation energy. So what happened is that the activation energy, that vertical line, has been moved to the left. So you can see as I shade that portion to the right of the activation energy, I'm shading that portion underneath the curve. In choice D, you can see there is definitely a larger fraction of the collisions that have enough energy to overcome the activation energy barrier. So this is the reason why choice D is correct. In choice D, the line that represents the activation energy for the reaction has been moved to the left. This shows exactly what would happen in the presence of a catalyst, a decrease in the activation energy, and now, as you can see, I've shaded that portion, a greater fraction of the collisions have enough energy to overcome the activation energy barrier. So we've already eliminated choices A and B because they tried to change the temperature, and there's a different appearance of the Maxwell-Boltzmann distribution curve. And then in choice C, they changed the activation energy, but they made it higher instead of lower. So correct answer to question 8 is choice D. Now let's move on to the last question in this packet. This is question 9. In question 9, it says, the rate of the reaction represented above increases significantly in the presence of a solid catalyst. Which of the following best explains this observation? So before I consider the 4 choices in question 9, let me show you a couple of the essential knowledge statements for topic 5.11 that are relevant to question 9. In order for a catalyst to increase the rate of a reaction, the addition of a catalyst must increase the number of effective collisions and/or provide a reaction path with a lower activation energy. So I'm looking for lower activation energy among my 4 choices in question 9. And also, this happens to be a solid, so in a solid or a surface catalysis, there can be a bond between the reactants or an intermediate and the surface. So I might look for a choice that implies there's a new bond with the surface, but definitely a lower activation energy is what I'm looking for. Okay, I'm going to start with choice A. In choice A, it says, the catalyst provides thermal energy to the covalent bonds in X2 and Y2, making them stronger and more difficult to break. So a catalyst should make the reaction faster, and if the bonds are more difficult to break, this does not suggest that there would be a faster reaction rate. It's actually more difficult to break those bonds, so that does not imply a faster reaction rate or a lower activation energy. So we can eliminate choice A. Now, moving on to choice B, it says the catalyst decreases the frequency of collisions between the X2 and the Y2 molecules. A lower frequency of collisions would result in a slower reaction rate. So again, we can eliminate choice B because we're looking for either a faster reaction rate or a lower activation energy. Now, choice C says one of the reactants binds on the surface of the solid catalyst, which introduces an alternative reaction pathway with a lower activation energy. And we would expect the catalyzed reaction pathway to have a lower activation energy, so at the moment, choice C looks correct. And then finally, looking at choice D, it says one of the reactants binds on the surface of the solid catalyst, which increases the activation energy of the reaction. And we would not expect the catalyzed reaction pathway to have a higher activation energy, so we can definitely eliminate choice D. So correct answer to question 9 is choice C, and again, it was that lower activation energy that was the main reason for choosing choice C. All right, well, this was question 9, the last question in this packet. So now we come to the part of the lesson where I give you advice to help you avoid common mistakes. So my first piece of advice is if you need more practice problems or more review for these topics, so 5.8 to 5.11, then you can check out my video, and this is included in the video description area, for topics 5.4 to 5.11, and that comes from my YouTube playlist that is organized by AP Chemistry CED units. My next piece of advice is what I normally say during this portion of the lesson, and that is to read the question carefully and make sure that you are answering the question that is being asked. My next piece of advice has to do with mechanisms and rate laws. Suppose that you are given a proposed mechanism and the equation for the overall reaction. You may be asked to write a rate law for the reaction that is consistent with the proposed mechanism. Be careful to avoid the following mistake. The order with respect to each reactant in your rate law should not be based on the coefficients of the reactants in the equation for the overall reaction. Instead, focus on the slow step. So the order with respect to each reactant should involve consideration of the slow step or the rate determining step of the mechanism. So if you are asked to write a rate law that is consistent with a proposed mechanism, the following guidelines are listed below. If the first step of the mechanism is the slow step, then you focus on the molecularity of the reactants in that slow step. You count the molecules of each reactant in the slow first step, and if a reactant has a coefficient of 1, then the reaction is first order with respect to that reactant. If a reactant has a coefficient of 2, then the reaction is second order with respect to that reactant. So take a look at these examples. Watch what happens if the student makes that mistake that I warned you to avoid. So here's a two-step mechanism, and there is the overall balanced equation for the reaction. So if a student who only looks at the coefficients of the reactants in the equation for the overall reaction says there's one molecule of NO2, there's one molecule of CO, then they would get the wrong answer for their rate law. Now, let's do what we are supposed to do. Let's focus our attention on the fact that in the slow step, there are 2 molecules of NO2 that appear as reactants. So if a student looks at the coefficients of the reactants in the slow rate determining step, then that student should get the correct answer. All right, let me show you one more example of that situation. So again, here's a two-step mechanism. Here's the overall balanced equation for the reaction. So a student that says, I'm just going to focus on the coefficient of 2 for the N2O in the overall balanced equation, they would write a rate law incorrectly. But if instead we focus on the fact that in the slow rate determining step, there's only 1 molecule of N2O, a student who does that should get the correct answer. So just a little piece of advice to make sure that you are successful on a question like this on the AP Chemistry exam. Now, if the first step of the mechanism is actually a fast equilibrium, and the second step is the slow step, that goes back to what I had mentioned about topic 5.9, the pre-equilibrium approximation. So you can watch that video that I mentioned, and you can go to topic 5.9 and look at questions 14 and 15 in that particular video. So I show you how to use algebra in order to perform a substitution, and the purpose of this substitution procedure is so that you can remove the intermediate from the rate law, replacing the intermediate with the reactants from the fast equilibrium in step 1. But you must show your work to earn credit on the AP Chemistry exam for making that substitution procedure. All right, my next piece of advice is if you are given an energy profile diagram that has only one hill, then the distance from the reactants to the top of the hill would represent the activation energy for the reaction. And the magnitude of the activation energy gives you qualitative information about the reaction rate, such as fast or slow. So a relatively small activation energy value is associated with a fast reaction rate, and on the other hand, a relatively large activation energy value is associated with a slow reaction rate. So suppose you have two hills. If you're given an energy profile diagram that has two hills in it, you can assume that the reaction proceeds through a two-step mechanism. And the relative height of the hills in that energy profile diagram allows you to compare the magnitudes of the activation energies for step 1 and step 2 and decide which one is faster or slower. So if you see small hill followed by big hill, then that would mean that step 1 is faster than step 2. On the other hand, if you see large hill followed by small hill, that would mean that step 1 is slower than step 2. And now, to remind you the difference between an intermediate and a catalyst, a reaction intermediate is formed during the reaction, so it's produced in perhaps step 1 and then consumed in step 2, but the initial concentration of an intermediate is unknown. On the other hand, a catalyst, which might be consumed in step 1 and then eventually formed in a later step, a catalyst is added to the reaction vessel at the beginning of the experiment. Therefore, the initial concentration of a catalyst is known. So in a reaction mechanism that involves a catalyst, it is common to see the catalyst as a reactant in step 1, which if step 1 is the slow rate-determining step of the mechanism, then the catalyst should appear in the rate law for the reaction. So even though a catalyst does not appear in the equation for the overall reaction, a catalyst can appear in the rate law for the reaction if it's part of that rate-determining step. And since a catalyst is consumed in the first step and then regenerated in a later step, the number of moles, or the concentration of the catalyst in the reaction mixture, should remain fairly constant as the reaction occurs. If a catalyst is in the same phase, such as gas or aqueous, as the other substances in the reaction mixture, it is a homogeneous catalyst, and one example of a homogeneous catalyst is an enzyme. If a solid catalyst is used, then the catalyst is not in the same phase as the other substances in the reaction mixture, and a solid catalyst is an example of a heterogeneous catalyst. If a suitable catalyst is added to the reaction mixture without changing the temperature of the reaction, the following statements are true. The number of effective collisions increases. A new reaction pathway occurs along the reaction coordinate, and the catalyzed reaction pathway has a lower activation energy than the uncatalyzed reaction pathway. With a lower activation energy, a greater fraction of the collisions will have enough energy to overcome the activation energy barrier. But remember that if the initial temperature of the reaction remains constant, then the presence of a catalyst does not increase the energy of the collisions. And the presence of a catalyst in the reaction mixture does not affect the following: the energy or the enthalpy of the reactants, the energy or the enthalpy of the products, or the difference in energy or enthalpy between products and reactants. Okay, so now we have come to the end of this lesson. In my next lesson, I'll give you the chance to review and practice topics 6.1 to 6.4. If you enjoyed this lesson, I invite you to like this video and subscribe to my YouTube channel. Check out the links in the video description area, which include the link to my YouTube playlist organized by AP Chemistry CED units. You can add your comments and questions below this video, and you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. Thank you for letting me be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Keep studying, and I'll see you next time on AP Chemistry Review and Practice.